Welcome to this explainer. Look, right now there is a massive architectural shift happening across the cloud-native landscape. We are actively moving from running short-lived, isolated tasks to deploying entire fleets of autonomous AI agents. But here's the catch. There's a huge gap between running a cool AI prototype locally on your laptop and actually deploying a robust, production-ready agent environment in Kubernetes. So today, we're going to bridge that exact gap. Consider this your complete technical briefing on how to architect, scale, and secure these non-deterministic digital workers. Here is a quick look at our roadmap. We'll start with the foundation, containerizing your workspace. Then, the brain, handling memory. Next, the fleet, covering autoscaling. And finally, we'll lock the whole thing down with the shield. All right, part 1, the foundation. Let's look at containerizing agent workspaces right down at the pod level to make sure our execution is totally consistent. So, the absolute crucial first step here is establishing your execution baseline. When you package an agent framework like AutoGPT, for instance, Docker gives you that nice, necessary isolation. But remember, an agent is basically a stateful singleton. It absolutely needs a digital workspace. You've got to map your Docker volumes from the host straight into the app/AutoGPT workspace directory to persist the files it generates. Oh, and here is a massive operational detail. You have to set headless browser equals true in your environment variables. No exceptions. If you try running a browser in non-headless mode inside these containers, it's going to instantly crash on you. Moving right along to section 2, the brain. Let's talk about memory and how we manage statefulness across sessions. Now, you're going to see a stark trade-off in how we handle an agent's memory as we push toward production. If you're just doing isolated dev work on your laptop, sure, use a simple local JSON file. You literally just bind an autogpt.json file right to your Docker container. Super easy, works great. But the second we move to Kubernetes, pods are ephemeral. If a pod gets evicted, boom, your agent gets total amnesia. That is exactly why enterprise fleets transition over to Redis-backed storage or maybe specialized vector databases. It centralizes everything, meaning your fleet retains that critical conversational context and semantic memory even if the underlying container completely restarts. Okay, section 3 is the fleet. This is where we get into orchestrating these isolated brains into a collaborative, auto-scaling workforce. Listen, if you try to scale your AI agents using standard Kubernetes horizontal pod autoscalers, you're going to hit a brick wall immediately. Why? Well, traditional CPU and memory scaling metrics are basically useless for AI agents. These agents spend like 99% of their time just sitting there waiting on I/O. They're waiting for API responses, LLM inferences, tool executions, you name it. So your CPU metrics will look incredibly low, even if you literally have hundreds of jobs piled up in the queue. To fix this, we absolutely have to introduce KEDA, the Kubernetes Event-Driven Autoscaler. KEDA is an absolute game changer here. Instead of relying on those useless CPU metrics, KEDA actually scales our fleet based on the pending queue depth. You can trigger scaling based on something like a Redis list length or even an AWS SQS backlog. The big takeaway for you here is that KEDA enables true scale-to-zero capabilities. If there are no tasks in the queue, it shuts the agent pods down completely, zero compute waste. But the second a new task hits, KEDA spins that pod right back up. So you've got a fleet. How do they actually talk to each other? You generally have two main architectural patterns to choose from here. First up is the supervisor pattern. This is where a central orchestrator assigns tasks to specialized worker agents. It is super easy to govern, but, and it's a big but, that supervisor pod will quickly become a nasty bottleneck. On the flip side, you've got the peer-to-peer pattern. Agents negotiate directly with each other. It's highly resilient, but you've got to watch out because it introduces this massive quadratic coordination overhead. We're talking n times n-1 divided by 2 communication paths. As your fleet scales up, that peer-to-peer chatter can just totally overwhelm your network. And now, we reach the climax of our briefing. Section 4, the shield. Let's dig into security and securing this entire system. We really need to talk about protecting your system against the terrifying reality of non-deterministic AI. Let me share a crazy war story from the platform engineering community. They call it the Pocket OS incident. Basically, a helpful little AI coding agent ran into a simple credential mismatch in a staging environment, and it decided to fix the problem. But because its reasoning is non-deterministic, it completely hallucinated a database error. In one single API call, it deleted a production database and all its volume-level backups. The agent thought it was just doing its job. It was looking for a plausible next step. That wasn't a model failure, guys. That was a massive failure of the platform's control layer. To make sure that exact nightmare doesn't happen to us, we have to start with identity and secrets. Credentials, especially those super powerful LLM API keys, must never, ever be hard-coded in your deployment manifests or static.env files. Instead, inject those API keys safely via Kubernetes secrets. And for a real production environment, those secrets need to be backed by external vaults, like AWS Secrets Manager or HashiCorp Vault. Plus, you've got to eliminate long-lived secrets and enforce really short rotation cycles. Think about it. If an agent goes rogue, you want its access to expire in minutes, not months. All right, this brings us to the 7 mandatory controls you absolutely need to govern agentic failure modes. Think of this as your ultimate production checklist. First up, identity. Agents need short-lived workload OIDC tokens, not shared service accounts. Second, authorization. Give them least privilege access right at the tool boundary. Third, tool allowlists. You need a versioned registry of allowed actions so an agent can't just wake up and decide to run kubectl delete namespace. Fourth, audit logs. Immutable storage that records every single prompt, tool call, and token. Fifth, rate limits. Set hard boundaries so orchestration loops don't accidentally run up a massive cloud bill. Sixth, rollback. You need a programmatic, tested way to revert agent behavior at 2 a.m. And finally, number 7, deterministic fallbacks. When an agent runs out of actual work and starts hallucinating tasks, your system needs to trigger a non-AI code path to hand control back to a human. So I'm going to leave you with this somewhat terrifying but very real question. If your autonomous AI agent decides to rewrite your infrastructure today, will your cluster actually say yes? Getting these controls implemented ensures your infrastructure is just as mature as the intelligence you're deploying on it. Thank you so much for joining this explainer. Keep learning, keep building, and we'll catch you next time.